NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we solve logarithmic inequalities when the base is between 0 and 1. We will follow a clean algorithm for two cases, log base of n less than 0 and log base of n greater than 0. Example: solve the inequality log base of n is less than 0, assuming 0 less than 1. Step 1. Apply the change of base formula and state the sign of log of a. Log base a of n equals the common log of n divided by the common log of a. Because 0 is less than a and it is less than 1, log of a is negative. Step 2. Multiply both sides by log of a. Since log of it is negative, the inequality reverses direction. Step 3. Convert to exponential form with base 10 to remove the logarithm. Log of n greater than 0 means n is greater than 10 to the 0, which equals 1. Therefore, n is greater than 1. That completes the first case. When log base of n is less than 0, the solution is n greater than 1. Example: now solve log base of n greater than 0 with 0 less than 1. Step 1. Apply the change of base formula again, and remember that log of it is negative. Step 2. Multiply both sides by the negative quantity log of a. The inequality flips to less than. Step 3. Convert to exponential form. Log of n less than 0 means n is less than 10 to the 0, which equals 1. Combine this with the logarithm domain n greater than 0. The solution interval is 0 less than n less than 1. Quick recap. For bases between 0 and 1, log of a is negative. That single fact forces the inequality sign to reverse when you clear the base. As a result, log base of n less than 0 gives n greater than 1, and log base of n greater than 0 gives 0 less than n less than 1. Start with the inequality. Log base of n is less than 1. Apply the change of base formula. Because it is between 0 and 1, log a is less than 0. Multiply both sides by log a. Since log a is negative, the inequality reverses from less than to greater than. Simplify the left and right. Use the monotonicity of the logarithm. If log x is greater than log y, then x is greater than y. Therefore, n is greater than a. Now, we proceed to the second case. Case 2. Start with the inequality. Log base of n is greater than 1. Apply the change of base again. And remember log a is less than 0. Multiply both sides by log a. Because log a is negative, the inequality reverses from greater than to less than. Simplify to get a comparison of logarithms. Use the same monotonicity rule of logarithms. Thus, n is less than a. Finally, log a is negative, the inequality reverses from greater than to less than. Simplify to get a comparison of logarithms. Use the same monotonicity rule of logarithms. Thus, n is less than a. Finally, apply the domain restriction for logarithms. N must be positive. Combining gives 0 less than n less than a. Summary of results. For log base of n less than 1, the solution is n greater than a. For log base of n greater than 1, the solution is 0 less than n less than a. N less than 1, the solution is n greater than a. For log base of n greater than 1, the solution is 0 less than n less than a. First, the example label. Then, the two target inequalities we will solve step by step. Part 1. Start with the inequality log base a of n is greater than -1. Step 1. Apply the change of base formula. Then write the inequality using common logarithms and explicitly note that log a is less than 0. Step 2. Multiply both sides by log, which is negative, so the inequality reverses. Step 3. Simplify. The log a cancels on the left. Step 4. Use the power rule of logarithms to move the negative sign into the argument. Step 5. Remove the logarithms, since the same base makes the log function strictly increasing. Step 6. Apply the domain restriction n greater than 0 and rewrite a to the -1 as 1 over a. Great. That completes the first inequality. The inequality is log base 1/4 of open parenthesis 2x minus 3 close parenthesis is greater than 0. Step 1. Restate the inequality. Step 2. Apply the change of base formula and record that the base equals 1/4, which is between 0 and 1. Then write log of 2x minus 3 divided by log of 1/4 greater than 0, semicolon, 0 less than or equals 1/4 less than 1. Step 3. Multiply both sides by log of 1/4. Because log of 1/4 is negative, the inequality sign reverses. Step 4. Simplify. The logs cancel on the left, and 0 times anything is 0. Step 5. Convert to exponential form and include the domain condition that the argument must be positive. Step 6. Evaluate 10 to the 0, which equals 1. Step 7. Solve the compound inequality. First add 3 to all parts, then divide by 2. First add 3 to all parts, then divide by 2. 3 less than 2x less than 4, which gives 3 halves less than x less than 2. Step 8. Write the solution set and visualize it on a number line. The set is open interval, 3 halves log base 1/6 of the quantity 4x minus 6 is less than negative 1. Step 1. Restate the inequality exactly as given. Step 2. Apply the change of base formula and note that the base equals 1/6 lies between 0 and 1. Step 3. Multiply both sides by log of 1/6, which is negative, so the inequality reverses. Step 4. Simplify the left side, leaving log of 4x minus 6 greater than negative log of 1/6. Step 5. Rewrite the negative logarithm using the power rule. Step 6. Since the same logarithm appears on both sides, drop the logs to compare the arguments directly. Step 7. Rewrite the right-hand side as the inverse of 6 to the negative 1, all to the negative 1. Step 8. Evaluate the expression, which equals 6. Step 9. Add 6 to both sides. Step 10. Divide both sides by 4. Step 11. State the solution set exactly as in the algorithm. The inequality is log base 1/8 of the quantity 2x minus 8 is greater than negative 1. We will follow the exact step order of the provided algorithm. For intuition, remember that a logarithm with a base between 0 and 1 is decreasing. That will be the reason why the inequality sign flips later, when we multiply by log of 1/8, which is negative. Step 1. Apply the change of base formula. We rewrite the left side as common log of 2x minus 8 divided by common log of 1/8. Also note the base is between 0 and 1. Step 2. Multiply both sides by log of 1/8. Since log of 1/8 is negative, the inequality sign reverses from greater than to less than. Step 3. The terms on the left cancel, leaving log of 2x minus 8 is less than negative log of 1/8. Step 4. Use the identity negative log of b equals log of b to the power negative 1. Step 5. Remove the logarithms. Since common log is increasing, we can compare the arguments directly. The right side becomes 8, and the argument of the left side must be positive. Therefore, 0 is less than 2x minus 8, and 2x minus 8 is less than 8. Step 6. Solve the compound inequality. Add 8 to all 3 parts, and then divide by 2. Now the problem statement, log base 1/10 of x squared plus x plus 1 is greater than 0. Step 1. Apply the change of base formula. This rewrites the logarithm as the common log of x squared plus x plus 1 divided by the common log of 1/10 is greater than 0. Step 2. Multiply both sides by log of 1/10. Since log of 1/10 is negative, the inequality reverses. This gives log of x squared plus x plus 1 is less than 0. Step 3. Convert the logarithmic inequality to an exponential bound. A common log less than 0 means the argument is between 0 and 10 to the 0. Therefore, 0 is less than x squared plus x plus 1, and that is less than 10 to the 0. Step 4. Split the compound inequality into 2. We have two conditions: x squared plus x plus 1 is less than 1, and x squared plus x plus 1 is greater than 0. Step 5. Solve each inequality. From the first x squared plus x is less than 0, which factors as x times x plus 1 less than 0, so the solution is between negative 1 and 0. The second inequality is always true because the quadratic has negative discriminant and opens upward. Intersecting both gives -1 less than x less than 0. To visualize the solution, look at the number line from -2 to 2 and shade the open interval from -1 to 0. Final answer. The solution set, D, is the open interval from -1 to 0. An interval from -1 to 0. We will solve a logarithmic inequality step by step, mirroring a standard algorithm. First, we display the example and the inequality to solve. Step 1. Because the base 1/3 is between 0 and 1, we compare exponents, but the inequality reverses direction when we move to the exponents. We rewrite 1 as 1/3 to the 0. Therefore, log base 1/9 of the quadratic expression is greater than or equal to 0. Step 2. Apply the change of base formula. Log base of b equals common log of b divided by common log of a. So we obtain a quotient with denominator log of 1/9. Step 3. Since log of 1/9 is negative, multiplying both sides flips the inequality. Thus we get common log of the expression is less than or equal to 0. Step 4. Translate the logarithmic inequality to exponential form and include the domain condition that the argument of the logarithm must be positive. Therefore, 0 is less than the quadratic expression, and it is at most 1. Step 5. Solve the first inequality on a number line. We mark 0, 1/3, 3, and 10/3. The quadratic x squared minus 10/3 x plus 1 has roots at 1/3 and 3. Because the parabola opens upward, greater than 0 occurs outside the roots. Step 6. Solve the second inequality x times the quantity x minus 10/3, less than or equal to 0. We highlight the interval from 0 to 10/3 inclusive. Step 7. Intersect the two solution sets. The overlap is from 0 up to, but not including 1/3, and from just above 3 up to 10/3 inclusive. Step 8. Here is the problem we will solve exactly as written. The inequality is log base 1/2 of the quantity, log base 6 of the fraction x squared plus x over x plus 4 is less than 0. Step 1. Because the outer logarithm has base 1/2, which is less than 1, the inequality reverses when we convert to exponential form. So the inner expression must be greater than 1/2 raised to the 0. Step 2. Any non-zero number to the 0 power is 1. That simplifies the inequality to log base 6 of the fraction is greater than 1. Step 3. Now remove the inner logarithm. Since the base is 6, which is greater than 1, the inequality direction stays the same. The argument must be greater than 6 to the first. Step 4. Subtract 6 as a single fraction over x plus 4. This gives a rational inequality greater than 0. Step 5. Factor the numerator. We need two numbers that multiply to -24 and add to -5. That is +3 and -8. Step 6. We'll solve the rational inequality using a sign chart. The critical x values are -4 from the denominator, -3 from the factor x plus 3, and 8 from the factor x minus 8. We'll mark these on a number line and test the sign in each interval. Therefore, the rational expression is positive on the intervals from -4 to -3, and from 8 to infinity. This also satisfies the domain of the original logarithms, because our transformation required the inner log value to exceed 1. So the final solution is x in the union of the open intervals -4 to -3 and 8 to infinity. In this example, we will follow the exact textbook steps to solve a logarithmic inequality. Find the bounds for the absolute value of x. Given log base 1/5 of the quantity x squared minus 4 is greater than or equal to -1. Step 1. Apply the change of base formula. That turns the expression into the common log of x squared minus 4 divided by the common log of 1/5 greater than or equal to -1. We also note that the base a is between 0 and 1. Step 2. Multiply both sides by log of 1/5. Because log of 1/5 is negative, the inequality sign reverses. Step 3. Simplify the left side. We obtain log of x squared minus 4 is less than or equal to negative log of 1/5. Step 4. Use the logarithm property. Negative log of b equals log of b to the power -1. Thus, negative log of 1/5 equals log of 1/5 to the power -1. Step 5. Remove the logs by monotonicity of the common logarithm and enforce the domain. Since the argument of a logarithm must be positive, we have 0 less than x squared minus 4, and it is less than or equal to 5. Step 6. Add 4 to all parts of the inequality to isolate x squared. We get 4 less than x squared less than or equal to 9. Step 7. Take square roots to solve for the absolute value of x. The square root of 4 is 2, and the square root of 9 is 3. Therefore, 2 is less than the absolute value of x, which is less than or equal to 3. To visualize the solution set on a number line, it consists of all x whose absolute value is between 2 and 3, including 3 but excluding 2. That is from -3 to -2, with -3 included and -2 excluded, and from 2 to 3, with 3 included and 2 excluded. Final answer: 2 is less than the absolute value of x, which is less than or equal to 3. In this lesson, we will prove a logarithmic inequality. We want to check if the statement 1 over log base of 7 is greater than 1 over log base of 5 is always true when the base is between 0 and 1. First, let's build intuition. For a base between 0 and 1, the log function is decreasing. We'll visualize y equals log base 1/2 of x as a concrete example. Notice how the curve goes down as x increases. Here are the values at x equals 5 and x equals 7. The y value at 7 is lower than at 5, meaning log base of 7 is less than log base of 5. Formally, step 1. Because 0 is less than a and is less than 1, the function x maps to log base of x is decreasing. Since 7 is bigger than 5, their logarithms reverse order, giving log base of 7 is less than log base of 5, and both values are negative. Step 2. Taking reciprocals of negative numbers flips the inequality direction. If x is less than y and both are below 0, then 1 over x is greater than 1 over y. Apply this with x equal to log base of 7 and y equal to log base of 5. Therefore, the original inequality is always true for every base strictly between 0 and 1. As a quick check, take it equal to 1/2. Then log base 1/2 of 7 is about -2.806, and log base 1/2 of 5 is about -2.322. Their reciprocals are about -0.357 and -0.43. So indeed, 1 over log base of 7 is greater than 1 over log base of 5. Example: we will find the domain of x for the function y equals log base of log base of log base of x under the condition 0 is less than a and it is less than 1. We strictly follow the steps shown in the solution. Step 1 states log base of x is greater than 0. This ensures the argument of the outermost logarithm is positive. Step 2 in the image converts this logarithmic inequality with base between 0 and 1. For bases between 0 and 1, exponential form reverses the inequality, giving 0 is less than log base of x and log base of x is less than a to the 0. Step 3 simplifies a to the 0 to 1. Therefore, we obtain 0 is less than log base of x and log base of x is less than 1. Step 4 splits the compound inequality into 2 lines and solves each. First line, log base of x greater than 0 implies 0 less than x less than a to the 0, which yields 0 less than x less than 1. Second line, log base of x less than 1 implies the log of x over log of a less than 1. Because log of a is negative, this gives log of x greater than log of a, so x is greater than a. The final domain is the intersection of the two results, 0 less than x less than 1, and x greater than a. Because it is between 0 and 1, the intersection is a less than x less than 1. Let's visualize that on a number line. Final result, the domain of x for y equals log base of log base of log base of x, with 0 less than 1 is the open interval from a to 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.